vertical line. We don't draw the shape of the lens as they have over there. So this would be the lens. Then we differentiate 2 points either side of the lens. We talk about the one point is F1, and we have an identical F1 point on the opposite side of the lens. F1 is the point where we find that, where's that diagram, convex and concave lenses? Not that one. No, not that one. That one. Where did I have the picture of a convex and a concave lens? Not there. Not there. Where did I have the diagram that shows the rays are converged and the rays diverge? Did I have one? It's not there. Okay. Okay, I don't know where it is. Never mind. Which one is it? That one? Oops, not that one. I have to go. There. No, not that one. This one doesn't want to move. Seriously, this is not possible. I have to use that one. There, okay, it's not that one. It's not that one. Oh, seriously. There, this one. Okay. People, the point here where all the rays come together is known as the focal point. Okay? And the distance from the focal point to the center of the lens is known as the focal length. Okay, so now I want to go to my ray diagram, and we are over there. Now, this then is the focal length, and F1 is the focal point. Okay, so that is the focal length. All right, and now we need to mark another point known as F2, and F2 is going to be exactly twice the focal length. All right. Now, when we use a convex lens as a magnifier, we hold the lens close to the object we want to have a look at. All right? We say the object, and I'm representing the object with this red arrow, the object lies between F1 and the lens. It lies close to the lens. Yeah, it doesn't have to be exactly in the half, just anywhere between F1 and the lens. All right, now, what are we going to see? Well, you've all worked with a magnifying glass. What do you see when you look at something through a lens? It enlarges it, okay? How does it work? What do the light rays do? Now, we are going to draw two light rays. I'll draw a black one and I'll draw a blue one. The first light ray that you draw goes from the top of the object parallel to the optical axis, and then it is bent through F1. Okay, that's the first ray. Remember, there are millions of rays. We are going to trace the path of two specific rays of light. So it will be this one, refracted through F1. Sorry, I've got a freehand line here. You need to use a ruler. Then, yeah, the second light ray just very simply goes from the top of the object straight through the center of the lens. All right? Now, the image is going to be formed where these two rays of light meet up with each other Are they going to meet up down here somewhere? Nope, why not? The lines are going apart. Where will they meet up? On the other side. So, here we can draw a line going back, and I'm sorry, this is freehand. And here we draw a line going back there. Where do we find our object or our image? What do we know about this image? Is it bigger or smaller than the object? Much bigger. It's enlarged. Is it upside down in relation to the object or upright? Upright. Okay, so have a look here. The image in a magnifying glass is enlarged because it's bigger than what the object was. It is upright because it's got the same orientation in relation to the optical axis. All right? And it is virtual. Now, once again, what is a virtual image? The light does not really reach the image. I can't project it on a screen. So when you look through the magnifying glass and you see the enlargement, is there really an enlargement? No, it's a virtual image. All right. Yes, yes. The magnification can be calculated as the height representing the size of the object in relation to the height of the image. You can take a ruler and you can measure it, or that proportion will also be there if you take that distance in relation to that distance. You can also work out the enlargement 2 times or 3 times or 4 times or 1.5 times, etc. Okay. That is the ray diagram representing the image formed by a magnifying glass. This is the diagram. Here we have the object. Okay. The object lies between F1 and the lens. There is F1. Okay, it's not very clear on the diagram. The 2 rays, the one that goes parallel and then is refracted through F1. F1 is over there. All right. And the other ray is the one that goes straight through the center of the lens. Yeah. No. If your object lies between F1 and the lens, you will always get an enlarged upright image. Yes, I think my diagram is not very accurate. It should probably be between F1 and F2. Well, now we'll come and have a look at those in a moment. Okay. Do you all understand what we've done? Yes. All right. Yes, you should, because we've done them in grade 10 as well. But I didn't understand it in grade 10. But do you understand it now? I think. Good. That is definite vooruitgang. Yes. All right, now, I've written up here on the board, draw ray diagrams for an object on F1, object between F1 and F2, object on F2, object beyond F2. Now, I want you to do this for a homework exercise, but please write this down as well. I want you have your optical axis, okay, and you have your lens. For each of these cases, I want F1 to be a distance of 3 centimeters from the lens. Okay? So F2 will lie a distance of 6 centimeters from the lens. Are you all with me? All right? Ne? This is the grid on which you are going to draw your diagrams. Okay. So this picture here is going to look the same for that one and that one and that one and that one. The only difference is going to be this one must lie on F1. In other words, for this one, the object must be 3 centimeters from the lens. Okay? and I want you to draw the object. Let's take it 2 centimeter high. In other words, the object is represented by an arrow that is going to be 2 centimeter high. Yes, no, the object in all of the diagrams is going to be a line 2 centimeter high. All right, now, the first instruction is on F1. So you will put this one there on F1, and you will draw 2 rays, as we had over here. That one in red, and the other one in blue, okay? Yeah. No, no. Still, the 2 rays run from the top of the object parallel to the axis, and that one is going to be refracted through F1 always, and the other ray will go from the top of the object straight through the center of the lens always. Okay. The only thing that is going to be different is my object is going to shift. Now, for the second one, they say the object must lie between F1 and F2. Let's say your object lies 4 centimeters from the lens. So you're going to take your object and you are going to shift it 4 centimeters. And you are going to draw the 2 rays again on a different diagram.
I forgot that you draw them in different colors of line.
No. Definitely not.
Let me try it. I'll do it correctly.
Okay, are you with me? Then the next one, object on F2. In other words, my object will be 6 centimeters from the lens, 2 centimeters high. You draw the rays, you find the image. And the last one, beyond F2, so make it on 8 centimeters from the lens. And then I want you to see what the image looks like for each condition that we have. Yes? No, you don't have to work the enlargement. Okay. All right. Yes? Yeah. No. No. We'll do practicals at a certain point, but I don't give you tasks to do because you're going to take them down from the internet, and it's just, my marking eventually consists of me sitting in front of the computer, typing in a couple of keywords, getting the article that you copied over, stapling it onto your task, giving you a note, and there we go. So no, I don't give you tasks. No, it goes quickly. When you type in the keywords, the correct one pops up easily. It's quicker to do that than to mark them.
How long did it take you before you found that?
No, immediately. Okay. Haven't you ever thought of doing that? Okay. Grade 8, 9s, 10s. Okay, all right, people, I want to go on. The next concept that we must have a look at now is something called the refractive index. It's a calculation. It's a little bit of math. Okay, people, we all know when light travels from one medium to another, if it's going to a slower medium, the direction changes because the ray bends towards the normal. For example, here we have air, okay, and here we have water. So what does the light ray do? It goes from the air in the water, it goes slower. So instead of going straight, it bends towards the normal. Okay, now we can go and work out for a specific medium the amount of refraction that will occur. Okay, and that is called the refractive index. Okay, it's a numerical value that can be calculated that will show how much the light will bend in a specific medium when it travels from one to another. Okay, the formula Refractive index is represented by a symbol n, and it's calculated by taking the sine, a lot of math, of the angle of incidence. So where's our angle of incidence? Between the ray and the normal. So there is the angle of incidence. Okay? So you measure it with your protractor, and then you have to work out the sine of the angle of incidence, and we divide it by the sine of the angle of refraction. So where's the refracted angle? Well, if that's the normal and that's the ray, there. It's labeled theta 2 in this case. That is the angle of refraction. So you put it in sine of angle of incidence divided by sine of angle of refraction will give me the refractive index. There's another way of working it out, because the amount of bending depends on how much the wave is slowed down. So if you know the speed of the wave in the one medium and the other medium into which it's going, you can use the speed of light in air, and you can divide it by the speed of light in that specific medium. They can give you they can give you that one, they can give you n, and they can give you that one, and they can ask you to calculate that one. Okay. All right. And then another way of looking at it, remember if we have a puddle of water there, and we have a rock lying there, and if you look at it from the top, the light coming from that rock is going to be refracted away, it's bent away from the normal, and it's going to seem as if the object lies somewhere there more shallow. Okay, real and apparent depth. Now you can use the real depth, and you can also divide it by the apparent depth, and that will give you the refractive index of that medium. Yeah, that one. Okay, real over apparent depth. Apparent depth will be less, so refractive index is going to be a whole number. Okay. Yes, I want to stop at that point for now.